The next topic that we're going to cover has to do with process capabilities and their relationship to histograms. First, what is a histogram? A histogram is a frequency distribution for a data set. It's a variable data set. It is a bar graph that shows the amount of variation in the process, and traditionally it is bound relative to your specification limits. It is effectively a control chart on its end for a period of time. So if you were to imagine taking a control chart that you have a sufficient amount of data on and pretend that each subgroup that you've plotted is representative of a pebble or a game piece for Connect 4 type game, and you tip the control chart from a horizontal view to a vertical view and let all the different subgroups that you've collected fall onto the ground and into a row, and you want to see what the distribution looks like. That is what a histogram is. It shows you how often any particular subgroup value occurred for a given set of time. Now with a control chart, what you see is how your data is doing in real time relative to how the data was behaving historically. So even one subgroup that is outside of control limits is going to be a cause for investigation. With the histograms, once you have that data and you want to analyze the actual data and put it into a histogram, you can actually find patterns within the histogram and learn from that. Now with a control chart, patterns or non-randomness is generally considered a bad thing. It is something that you're going to need to investigate and try to get out of your system if at all possible, because that is a source of variation that you have the ability usually to control. Patterns in histogram are not necessarily a bad thing per se. There's something that, in fact, the fundamental things we learn from it come from the fundamental pattern. Measurements, and this is really important, measurements tend to cluster around the middle of the distribution with less data around the tails or the edges of your distribution. Within the universe, property of the universe, things tend to cluster towards the middle. Most of the mass of the solar system is in the sun. It's in the center of the solar system. Most of the mass of the galaxy is within the center of the Milky Way galaxy. When you pour coffee when you pour coffee creamer into your coffee, and while it's spinning, you'll probably notice that most of that tends to go towards the middle. If you go shopping and you see the lines at most shopping markets or something like that, in general, you'll find, all things being equal, that people will tend to go towards the center lanes. It is a property of the universe, and we leverage this. The fact that all things being equal, processes will tend to cluster towards the center and taper off from there at a very predictable rate. If at any time a distribution does not cluster towards the middle or has a bias towards the one side or the other, or some other pattern occurs, that is cause for investigation, usually a source from non-random variation. So what are some of the patterns that you can find within a histogram? The first example on this particular slide is the truncated distribution indicates part of the distribution has been removed through 100% inspection, or there is a natural limit to the process. So either somebody's fudging with your actual data in terms of getting rid of stuff. Maybe you have a checking machine that has 100% inspection and it just kicks out anything that is above a certain value or falls too far below a certain weight measurement or height measurement or something like that. So that's an indication of 100% inspection, why you might see this in a histogram. The other way you might get the truncated histogram if there is a natural limit to a process. For example, if you do tensile testing, certain materials, in fact, you can actually verify that a material is in fact what you think it is based on certain materials' properties on when its breaking point is. certain types of steel, when you do tensile testing, they will snap at a certain amount of force or amount of pull. And if they don't, that means you're probably measuring the wrong material, or the conditions for the test were not correct. Maybe the temperature in the room was wrong or something like that. Whereas other materials, like aluminum, don't necessarily have those same natural places of failure, natural tensile testing limits. A flat plateau on a histogram, that's the second example in the slides, may indicate that there's no defined process for producing your part at all. There are measurements possibly coming either from multiple processes, or you're just not able to make in any repeatable manner the production of whatever product you're trying to give to your customer. Your customer has certain tolerances. You're just not able to produce it in any relative rate, and you're almost lucky to, or you need 100% inspection to find the good ones amongst the bad ones. If you're shipping everything, regardless of actually checking this, you're probably giving your customers it's hit or miss on the quality of whether or not it even meets their specifications. The last pattern in the histogram that we see in this particular slide, separated with twin peaks, if you see two of these bell curve shape items, two of these natural distributions, that indicates you're measuring two distinct processes, things that should not be measured together. Maybe you are mixing the data from line A in your factory with the data from line B. Even if line A and line B have what you think are the same equipment and has all the same factors, and you've set it up exactly the same way, but then maybe line A was not assembled correctly, or line A has some problems or some maintenance issues that aren't being taken care of, or there's the operators or something is happening that is different about the two processes. Going forward, to be able to do proper process control, to be able to statistically control each line, you need to separate the two processes. You need to find out what those two processes actually are and separate them. Now, it doesn't just necessarily mean twin peaks. You could have triple peaks or quad peaks. You could have multiple peaks indicating that you are mixing together measurement data that should not be combined. In this next slide, we see a couple of other patterns, a few other patterns that could come up when you are viewing your histogram of your collected data. In this case, we're looking at the skewedness and the kurtosis of your distributions. Measurements that tend to cluster to one side or the other is called skewed data, data that is biased towards one side or the other. If you have more data tending to cluster towards the right of your center line, of your process mean, then that indicates a positive skew. Whereas if it is going more towards the left side, that's indicating a negative skew. And all things being equal, we would not expect there to be a skew. It would be up to you to investigate why you have a skew. Either there's a tendency, an unnatural tendency, that people are overfilling a item or underfilling an item, or maybe some set of equipment is biased towards one thing, or maybe there is some other process, natural tendency to be that way. But you do need to find out what that natural, that unrandom variation is that's causing this. Kurtosis is a measure of how peaked or flat the distribution is. Ideally, you'd have all of your data come out to be exactly what your target is, but that's not possible. The more likely you are to be able to hit that target, the more positive of a kurtosis you have, whereas the less likely you are within a given distribution to be able to hit that center line, to cluster towards the middle, the more negative your kurtosis is within your distribution. Okay, to sum it all up, with regards to histograms in particular, what are some of the advantages and disadvantages? Advantages of using a histogram is that it can allow you to find the very nature of the distribution. So you can tell whether or not there is some sort of bias, or there is some sort of non-natural or random variation that is forcing your data to not behave how we would refer to as normally. It helps us also determine, depending on what type of pattern we see in the histogram, where the data is coming from. It lets us see that there is data coming from more than one source, and then we can begin to act upon that. However, just because you see a pattern doesn't necessarily mean what that pattern is. You don't necessarily know how to interpret that without actually going and further investigating. There's not a clear pattern just because you can see something there. Useful tip, kind of like with Pareto charts, you're definitely going to want to see what your Pareto chart looks like now, what your histogram looks like now versus what it used to look like given a different data set, or if there are changes in your histogram over time. You must have sufficient readings to plot a histogram. If you do not have sufficient readings to plot a histogram, your histogram will be effectively worthless. 3 points does not make a good histogram. You want as much, unlike with control charts where you want a representative sample, histograms you want as much data as you possibly can, which usually corresponds to the control limits, but more data is more better for histograms. So you want to be able to have enough data to run them. You want to be able to run before and afters when you're doing quality initiatives or you believe something has changed. And you definitely want to look for unusual patterns. Unusual meaning things that are happening different now than used to happen, but also just if this is the first time you're running a histogram on a particular process, you want to see how this histogram behaves relative to the normal histogram, which is that evenly shaped, clustered in the middle bell curve histogram. Now, highly related to a histogram is process capability. Process capability is a way to determine whether the process is capable of producing a product that conforms to your customer specifications consistently. So if you want to be able to determine this, you run a capability study. Capability studies are performed on statistically stable processes. That doesn't necessarily mean in spec processes. It means processes that are in control. If your process is currently out of control because your most recent subgroup is out of control, or you have a lot of out of control conditions within your histogram or your data set that you're doing right now, you cannot do a capability study. It is a meaningless capability study because your process is in a state where it is highly likely that it is currently shifting. Therefore, you don't know if it is capable at that point. The objective of process capability study is to establish a state of control over manufacturing processes to be used in maintaining the state over time. In other words, it is a way, an industry standard way that you can give yourself an objective number grade that you can benchmark yourself against, that you can compare both the way you are versus how you used to be, how capable you used to be versus how capable you are now, as well as being able to compare yourself to other other companies or enterprises producing the same things that you are with capability, who are doing capability studies. So you can actually, to a great extent, use this objectively as a measure of how capable you are of producing a given product. So how do we measure the capability of a process? We have some key indicators that we can use to indicate how well our process or how capable our process is. CP is one of the most commonly used numbers that is calculated, and that is the process capability index. How do we calculate CP? CP is the difference of your upper spec minus your lower spec divided by 6 times the standard deviation of the data within that data set. So it is your upper spec minus your lower spec over 6 sigma. That is very tightly related to your control limits. It's similar. You're using your sigma to determine your spread, plus or minus 3 standard deviations from your process center line, and you're using your spec limits to see where you are, or using the spec limits to get an idea of within that standard deviation where you fall, within that magnitude. When you calculate all of your values, when you calculate your CP, upper spec minus lower spec over 6 standard deviations, estimated in the same R-bar over D2 method that was done for your control limits, you will get a range of values. In general, the higher the CP, the better off you are. The lower the CP, the less capable your process is, the worse off you are. If your CP equals 1.0000, that means that in an ideal world where you were producing most of your product right on your center line, if that were to be the case, 99.73% of your data would fall within specifications, within plus or minus 3 standard deviations from your center line. Your plus or minus 3 standard deviations from your center line would be 99.7% of your data. If your CP is less than 1, that indicates then that less than 99.73% of your data is falling within your upper and lower spec, or even if you were perfectly centered and most of your data was falling right at your ideal spot, you would still be producing a lot of bad product, more bad product than would be considered statistically capable. Further, if your CP is greater than 1, that means you are capable of producing at a higher peg than 99.73% of your data within spec. More than that, more than 3 standard deviations on either side of your target could theoretically fit inside of your upper and lower specifications defined by your customer. In fact, if you want to quantify this, if your CP were to equal 2, that would mean that in theory, exactly twice as much of your data would fall exactly within spec than it would if you had a CP of only 1. So you are twice as good, or you produce half as much waste, or you could theoretically produce half as much waste if your CP equaled 2 versus if your CP equaled 1. Now you may notice on this particular slide number 4, unlike the other 3 slides we saw previously, there's something that's pretty obviously, or at least should be obviously glaringly a problem here. Okay, so you could theoretically be producing twice as much good product than you would if your CP is 2 than if your CP was 1. However, that doesn't necessarily mean you're producing within specs, and it doesn't necessarily mean that you're not in a situation where you are close to start to be producing data that's out of spec. In this example, all of your CP equals 2, but all of your data is clustered towards your upper specification limit. If your process starts to shift a little bit towards your upper spec limit, you're going to be starting to produce a lot of bad data, a lot of bad product very quickly. Whereas if you were targeted with a CP, as it was in the previous slide, equaled 1, and you were targeted perfectly on your center line, on your X-bar, X double bar, your grand average, you would not necessarily be in that case. So CP as an indicator is not enough to determine whether or not you are capable of producing the product that you say you're able, or that you are trying to produce for your customers. If we want to determine the capability of our process, we need to introduce another metric that can tell us if we are not only capable of producing within plus or minus 3 standard deviations, but if we are targeted, meaning if we are centered at wherever we want our ideal output to be. CPK is the process capability index with centering, with process centering. The function for CPK is the minimum of one of these 2 separate calculations. Either it is your upper spec limit minus your process grand average divided by 3 standard deviations, or it is your process grand average minus your lower spec limit divided by 3 standard deviations. And again, the sigma here is estimated as the R bar over D2 method. So the slide on the left is the exact same slide we saw the exact same histogram we saw a couple of slides ago, where the CP equaled 2 in this case. However, CPK, because we are off-center, is far less than 2. In this case, we are not capable, or not very capable. If the process is centered in the process average, matches with that target, if your CP equals your CPK, you are capable. You are as capable as you can be, or with that level of CP. So ideally, you want a very, very high CP value, and you want the CP value to equal CPK. Now, most industry standards isn't not so much. It's the tendency for most customers is the benchmark is 1.33 CP is usually considered very capable. That's where you want to shoot for if you started off with either a marginally capable process or a completely incapable process. CP of 1 is usually not sufficient. I mean, more is always better in this case, but that's what most people tend to shoot for. But if you have a higher CPK, that's great. That means you're just less and less of your stuff is falling out of your customer specs. And you always want to, or you ideally want to have that equal CPK. A lot of regulatory industries and a lot of the government, when they require capability, they tend to only ask for CPK, but that really doesn't give you the full view of the story. You really need to have both CP and CPK, and we'll talk about that a little bit more later. So we're going to demonstrate an example once in a scenario where we've already made our control charts, so we already have all of our calculations that have been done for us. So if we go back to our Xbar-R example we did earlier, we had an X double bar, a grand average of 6.68, and we had an R bar value, a grand average of our range, to be 0.2. And we're going again, this is the pencil manufacturer that we were dealing with earlier. The specs for the pencil diameter is 6.7 millimeters plus or minus a half a millimeter. The upper spec is therefore 7.2, the lower spec is therefore 6.2. The standard deviation that we got from our Xbar-R chart previously was the R bar over D2 method. D2 is a constant from a lookup table. R bar is the calculated grand average of our ranges from that example. In this case, it was 0.2. 0.2 over 2.326 equals a standard deviation of 0.086. That's one standard deviation. That's one measurement of volatility within our process. Once we know our spec limits, we know our grand average, and we know our value for calculating sigma, we can then go ahead and plug and chug. The function for CP is the upper spec minus the lower spec over 6 standard deviations. Therefore, that's going to equal, in this particular example, 7.2 minus 6.2 divided by 6 times the 0.086, and that equals a value of 1.94. That's our CP. That means that our process tends to run tightly. We're almost twice, in theory, we could be producing twice as good as, or almost twice as good as if you had a CP of 1. Calculating CPK, we need to take the minimum value between the upper spec minus the grand average over 3 standard deviations, or the grand average minus the lower spec over 3 standard deviations. So we calculate both of them to find out which one of these are lower. 7.2 minus 6.8 over 3 times 0.086, or 6.68 minus 6.2 over 3 times 0.86. So either the CPK is going to be 2.01, or the CPK is going to be 1.86. 1.86 is lower than 2.01, therefore the CPK is 1.86. Okay, now that we have calculated CP and CPK, what does this mean? The CP value is 1.92 4, which is pretty good in most objective standards. Now, I have no historical context. I don't know if this is better or worse than you used to be doing, nor do I know how your competitors are doing. But at least I know that objectively you're doing what most industry experts would say you're doing pretty well on your capability, your CP. And CP is close to CPK, meaning you're pretty close to targeted where you want to be. Your process average is close to the target. You have a very high value, you have a near 2 for CP and CPK, therefore you can make a pretty safe assumption that your process is in fact capable of producing product at a very high peg, at a very high rate. If you were putting the data from your control chart or your data from your check sheets into WinSPC directly, WinSPC has the ability to not only calculate your control limits and determine whether or not you're currently in control, it can in real time calculate the values for CP, CPK, and many other indicators such as the performance indicator PP and the performance indicator with targeting PPK, which is beyond the scope of this particular course, but we calculate many different types of statistics, and all of this can be calculated automatically in real time, and it can be shown either to the operator or it can be mined afterwards and analyzed in our analysis tool pack as well. It further bears mentioning that even if you have a high CP and CPK, you probably still want to look at your control chart, and you're also going to want to look at your histogram. Because to get a complete view of the story, you really want to put all of these numbers in context. You also want to see how your capability is now versus how it was in the past. You want to be able to run these numbers over time to see if your process is falling or your process is improving. So a summarization of the advantages and disadvantages of process capability analysis. Why do we use it? We're using the advantage to it is used to find whether the process is capable of consistently producing parts and products that are conforming to specifications. It gives us an objective grade and a way to do that. Disadvantage is that only when the index is used for analyzing the process capability, you can't just use CP. You can't just use CPK. You need to use these things in context. You need to use these tools with other factors. You need to be able to both say, is CP high? If so, is it close to CPK? And then whether or not it is, you want to be looking at the control charts and the histograms to see where that actually falls. You also want to be able to compare that from the way it is now versus how it has been in the past to see if you're improving or getting worse. You can only run these capability parameters, the CP and CPK, if your process is statistically stable, meaning your process is currently in control and has been fairly in control for the data set you're running the capability analysis on. In general, the higher the CP and CPK values, the more capable your process actually is. So we actually have an exercise for you to be able to calculate your capability indices that pretty closely follows the example that we did earlier. This time we're going back to our radio example, the sound output for radios, 80 decibels plus or minus 10 decibels. The capability indices for this we're going to calculate. We already knew our grand average is 83.5 when we did our control charts. We know our R-bar value is 6.5. We're going to use the R-bar over D2 method with D2 constant when using a subgroup size of 4 to calculate our sigma value or estimate our sigma value. We're going to calculate CP, which is the upper spec minus the lower spec minus, divided by 6 standard deviations. We're going to use CPK, which is the minimum of the upper spec minus the grand average over 3 sigma, or the grand average minus the lower spec limit over 3 sigma. And we're going to take the minimum value of those two to calculate our CPK. And then we're going to go ahead and actually determine what this means for our process, or how this relates, how capable our process actually is. And here's the solution. So we see that the sigma value, the standard deviation, is 3.16. our CP value is 1.05. Our CPK is the minimum between 0.68 and 1.42. We throw out the 1.42, so our CPK is just 0.68. 1.05 is very, very marginally capable, even if you are perfectly targeted, and based on the CPK being less than 1, you are not targeted, so your process is not capable. You are going to be producing a lot more bad product than your customers would probably be able to would be happy about receiving. Now, you know that you're incapable. You don't know if you're incapable maybe because you're biased towards your upper spec or biased towards your lower spec. That is beyond the scope of your capability analysis. And then you need to go to your histogram and you need to go to your control chart to actually get that information. But as far as just having an objective grade that you can benchmark yourself and others can benchmark you by, your process in this particular example of radio manufacturing is not capable. The last of the SPC tools that we're going to be covering in this class is the use of scatter diagrams. What is a scatter diagram or a scatter plot? It's a point graph of measurements from two variables, and you use this point graph of measurements from two variables to find whether or not there is a relationship between those two variables, and if so, what is the nature of that relationship. When you plot a scatter diagram, you will be able to determine if there is a relationship of some kind between the two variables that you've chosen to plot against each other. So if there is a positive correlation, that is equivalent of saying there is a tendency that an increase of one of the two variables correlates with an increase of the other variable. If you have a negative correlation, that means if you increase one of the variables, that will decrease the other variable, or there is a decrease in the other variable, and vice versa. So the increase of one shows a negative correlation with the other variable. If you have no correlation at all, the increase of one does not show any correlation to any increase or decrease in the other variable. It's just random. And you can use tools that can draw, or you could calculate yourself a best fit line to determine graphically what that scatter line is. People, for most scatter plots that you do in normal situations outside highly regulated or highly problematic areas where you really need a very high level of certainty, you can actually usually eyeball this. You can usually just look at the scatter chart and say, yep, that looks kind of like there's a positive correlation. I'll throw it into Excel or use a tool I have to go and do the correlation to quantify it, but no, as one goes up, the other one tends to go up as well, or go down, or there's no relationship at all. Now, depending on how much data you have and how closely you can tie the correlations to each other, the individual points, you may be able to tell, even if it doesn't look like there's a correlation, if actually there may be a subtle correlation. But that's beyond the scope here. What's important to recognize is if there is a relationship, it should be able to be determined from a scatter diagram. We're using if anybody remembers from algebra, the equation of a line. It's y equals mx plus b. M is the same thing as your r value. It's the coefficient, or how fast or how much a value is either sloped up or sloped down, rise over run, if there's any slope at all. Okay, so overall view of a scatter diagram, what are the advantages and disadvantages? Advantages, you use it to find whether or not there is a relationship between two distinct variables. The type of the relationship between the two variables can be determined if it's either a positive relationship, a negative relationship, or no relationship at all. The disadvantage, and this is really important, is that Just because you see a correlation, that does not mean that one of those items caused the other item to occur. Correlation is not causation. Just because you see that your some measurement is going out of whack at the same time that something else is happening doesn't necessarily mean one caused the other. And that's a really very extremely important thing to remember. You need to take the human element and actually do a design of experiments to see which item caused the other item to occur, which if there maybe both of those items are the result of something else that happened, and it is your job to actually determine what that is. Correlation is not causation. It is merely correlation. It gives you a place to start to see that there is some kind of relationship there. To wrap things up, we're going to talk a little bit about some of the things that you should keep in mind, things that you should do during an SPC implementation of any kind, and things that you should not do during an SPC implementation or a WinSPC implementation for that matter. So some do's first, things you should absolutely do during implementation of statistical process control in your facility and in your environment, in your production environment. You do want to use SPC for improving your process. I mean, if you're not going to use it to improve your process, if you're using it maybe for regulation, then you're not really going to get a whole lot of return on investment on the effort. And if you're just going to be plotting control charts, and you're not going to actually be doing anything with these control charts or with these check sheets for all that matter, you're wasting your time. So you want to use SPC for improving your process. You want to plot control charts to monitor ongoing processes so you can respond when things begin to shift or when some non-random variation begins to act on your process. You want to look for those out of control indicators so that you can react to them and investigate and try to make things better, improve your process. And you want to analyze the process for assignable causes, meaning any non-random variation in your process when the process does go out of control. Things you do not want to do, you do not want to just plot control charts. You do not want to adjust your process when you don't need to bring it under control. Otherwise, you become the source of variation. The process would actually behave better if you had left it alone than trying to adjust it while the process is in statistical control. Do not confuse control limits with specification limits. They are not the same thing. Control limits is the voice of your process. It comes and is calculated from the data itself. Specification limits comes from your customers, be it internal or external. If you go out of control, that means your process is not statistically in control. Your process is likely changing or there's a assignable cause acting on it. If you're out of spec, that means that you've actually produced bad product. Do not just look at a CP value when you're doing a capability analysis. That only tells you if you're theoretically capable of producing within control. It doesn't necessarily tell you that you're producing anything within spec. You need to run CP and CPK, which is really easy to do when you're using a real-time software package like WinSPC, as opposed to doing things by hand. And this is a overview or a recap of the SPC tools that we covered during this training video. Check sheets, those are used for data collection for specific processes so that you can begin evidence collection and begin initiative with evidence of a quality improvement program. Pareto charts help you prioritize which of those items in your check sheet should be the vital few that you should focus on, and using the Pareto rule, you'll be able to focus your time most efficiently for the best bang for your buck. Cause and effect diagrams allow you to brainstorm based on the 4 M's, the possible causes of the issues determined in the check sheet and prioritized in the Pareto chart. The 4 M's, again, are man, material, machine, and method. Control charts are used to monitor and control ongoing processes in real time, ideally. Histograms can be used with the data from the control charts to determine the nature of the distribution of the data. All things being equal, everything should look in a bell-shaped curve. If it's not that way, you need to go ahead and investigate why. Capability studies tells or allows you to grade yourself and benchmark yourself to find the process capability and performance of your actual process. Are you able to produce what your customers are looking for you to produce? And a scatter diagram can allow you to find whether or not there is a relationship between variables for data that you are collecting, if there is a relationship at all, and if so, what is the nature of that relationship. Doesn't show you correlation, but it does allow you to see if there is a relationship and then begin to act upon that. Thank you very much for watching and participating in this SPC training class video. Certainly if you have any specific questions, I do encourage you to contact the DataNet Quality Systems Product Support Help Desk. We'd be glad to answer your questions. You can also go ahead and contact our sales department. They can give you a wonderful overview of SPC and how it might be used in your implementation. If you were using this as a refresher, I hope we were able to give you a good view of SPC and how you may use this in your actual process and how it may relate to use of WinSPC. And if this isn't a refresher, this is the first time you've ever seen this stuff, I hope this now gives you an understanding of why SPC and why you would want to use statistical process control in your environment.